Okay, so what I want to do is I want to go over exam 1. Since I circled the answers to the multiple choice questions, then if you have questions you can ask me about them. But let me go over the problems. There was 5 problems. You had to choose 4 of the 5 to be graded. So the first one, you had a sphere, and we'll say it's of radius r. You charge it so that the electric field and I should say the magnitude of the electric field is E. Then you take a wire and connect it to a second sphere a great distance away, and it's initially uncharged. So we'll call this R1. This sphere is radius R2, and you connect them with a wire. We're going to assume that the distance between the spheres is great compared to their dimensions, even though this figure is not to scale. And now I want to know what is the electric field afterwards. Okay. I want to know the electric field on the surface of the smaller sphere. So I want to find the electric field on this one. So first question is, can we figure out the charge on this one? These are empty conducting spherical shells. So I can always write the electric field as KQ over R1 squared. And I can call this Q1. So realistically, if I wanted to solve for a Q1, I could. Okay, the initial charge on this one was 0. So total charge we'll call Q1. That's the total charge that we have. Now we're told that the volume of the uncharged sphere is half the volume of the first sphere. So since volume is proportional to radius cubed, without me doing a lot of math, the radius of the second cubed has got to be equal to 1/2 to the 1/3 R1. In other words, the radius of R2 is the cube root of 1/2 times R1. That we know. So at least we can say that. Now, when we connect them together, charge will flow between them until they're both at the same potential. And I'll use the subscript final here to denote this is the potential when they're charged. Oh, I'm sorry, when the system reaches equilibrium. Of course, we can write the potential on the surface of each of these spheres because they're conductors in the following way. K Q1 final over R1 equals K Q2 final over R2. Which means Q1 final over R1 equals Q2 final over R2. So, these K's can cancel. So I have that relationship. Okay. So I can write the following. I can say R2 Q1 final equals R1 Q2 final. Now what? I have 2 unknowns. But I do know that Q1, already here, has to be equal to Q1 final plus 2Q final because I know charge is conserved. So the total charge in the 2 spheres has to be equal to whatever I started with. So let's say I write Q1 final as Q minus Q2 final. Then I can take this and substitute it up here. Oops. So really right now I can solve for Q2 final. Okay. Now I'm gonna skip all the math and just give you the final result. Okay. The final result is that's Q2 final. Okay. Now Q1, I'm sorry. I should write as Q1. Now Q1 is going to be E times R1 squared over K. Based on what we had initially. So I can put down the expression for Q1 up here. Now, what's the electric field on this guy? What is the electric field on this guy if this is the final charge? Well, it's going to be K times Q2 final over R2 squared. A Q2 final is this. But I want to write Q1 in terms of E. These K's cancel. So I get E times R1 over R2 squared divided by 1 plus R1 over R2. So the last thing then is to plug in what R2 is. R2 is 1/2 to the 1/3 R1 oops. So the R1s cancel, and then you get the following. And then you can further simplify it if you like. Okay, and then the rest is just algebra to simplify it. So I'll leave it at that. The next question is this. If I put a charge halfway between them, let's say, and I probably should have said disconnect the wire, but let's say I put a charge halfway between them, which way is it going to move? Now this charge is outside these two. If they're both at the same potential, okay, if these are both at the same potential, and this is a bigger sphere, this has to have more charge on it than this one. This guy is equidistant between this sphere and this sphere. So if this has more charge on it, the force on this one, the force between these two is going to be bigger than the force between these two. And if they're all positively charged, the repulsive force this way is going to be bigger than the repulsive force that way. So this is going to move towards a smaller sphere. So a lot of people put that down, but they didn't explain correctly why it would go towards a smaller sphere. All right. Okay, for the second problem, Part 2A wasn't well worded. So what I was looking for is 1, did you apply Gauss's law? And 2, did you integrate to find the total charge? This was a cylinder, and so if you use Gauss's law, sorry. So it wasn't a well-worded problem. So what I looked for is, did you integrate this? You're given a density that was given as AR to the 4th, distributed over a rod. So really what you got to integrate is over the cross-sectional area of the rod. And if you do that, if you remember, you just got to do rho times 2 pi r dr from 0 to whatever, and I'll put r primes here. And then you integrate to whatever your r is. If you're inside the cylinder, then this would be an arbitrary radius. But if you're outside the cylinder, this would be the radius of the cylinder. Okay. And then this integral ends up being easy because it's just going to be 2 pi r l e. So really I was just looking for you to apply, and again, the problem wasn't well worded, so I was looking for this, and I was looking for people to write this. And a lot of people just didn't integrate. They're doing density times area. They would do density times pi r squared, and you can't do that because the density is not constant. So that's all I was looking for, and the reason why I'm not showing you more because I didn't do a good job really wording the problem. Okay, and so if you did this, if you set this up, I give you credit for it. If you set this up, I give you credit for it. Okay. Now part B, you want to define the flux through a square of side L that is parallel to the xy plane. So let me draw a picture. And so let me draw the rod along the x direction. And I'm going to draw a plane above it. This is going to be hard to do. Okay, it's not the greatest picture. And what you want to do is calculate. You want to calculate the integral of E dot n dA. The electric field due to a rod, and I had a mistake in the exam, so the electric field due to a rod is going to be K lambda, 2K lambda over r. And the factor of 2 is missing on the exam. Okay? And it's pointed radially outward from the rod. So electric field is radially outward from the rod, okay? So let me draw a better picture. Here's a plane, and here's an electric field vector like this. And this distance is going to be the plane is the distance d above the rod. And we'll call this x. So this distance is x squared plus d squared square root. Okay. So this r then is going to be the square root of x squared plus d squared. Because r is the distance from the plane. Okay, this is the distance from the plane. So E, the magnitude, is going to be this. I can write it that way, okay? And if I go in this direction, if I integrate it in this direction, in the y direction, the field's going to have the same value because it's the distance from the rod, right? The field depends on the distance from the rod. So whether the rod's like this, so anywhere along the rod from this end of the plane to this end of the plane, the field will be independent of x, independent of y if I choose to write it like that. So what I can do then is when I integrate this, my dA, what's my dA going to be? Well, the field's going to vary in this direction, but not in this direction. So I can write this as this dimension, which is d, or L, sorry, and then times my x, my dx. So our dA is L dx. And then I got to consider is E dot n. The normal to the plane points downward. The field points essentially upward. So you have a normal vector that's this way. All right, so you have a normal vector that points this way. An electric field vector that points this way. This angle is bigger than 90. The component of the electric field along the normal is basically the z component of this. So if I know this angle theta, then it's just the z component. So E dot n, whoops, E dot n is going to be this times the cosine of this angle, or this angle, which is going to be d over this. So my expression for the flux is going to be 2k lambda times d. This times this gives you x squared plus d squared. And then there's a L dx. And then you integrate from minus L over 2 to plus L over 2. And that's it. That's your integral. And actually, that's an integral you can do. Okay, but I didn't want you to do the integral. All right, number 3, we had a particle in an electric field, and we had to find the velocity as a function of time if we're given the initial velocity and the mass of the object is m. So first of all, I got to find the acceleration of this thing. So the acceleration, well, first we got to find the force to find the acceleration. We use Newton's second law. So A is Q E over m, and E is given by that expression. So we'll write it as Q over m times 30I plus 40J volts per meter. Of course, A is dV dt, and dV is a dt. You know that. So I have to integrate. Let me integrate both sides. If I integrate both sides, I'll get V is the integral of a dt. Now, this is an easy integral because this acceleration is constant. And so I'm just going to get Q over m times 30I plus 40J. And the units will come out to, when I plug in everything, it will come out to meters per second. Oh, there's a T here, sorry. I won't put the units in. And there's a constant. What's the constant going to be? Well, it's going to be my initial velocity. It's going to be this. Really, that's it. If you want to rearrange it, you could. You can write it like this. So you can write it like that if you wanted to. The next question is calculate the work done by the electric field between 0 and 2 seconds. And really there's two ways of doing this. You can integrate this to find the displacement vector and multiply by QE. That's one way. The other way is to take the change in kinetic energy, because the work energy theorem says the work done is equal to the change in kinetic energy. I want to do it this way. It's easier. Because I can figure out V at 0 and V at 2. And I just find the change in kinetic energy. So V at t equals 0 is just this. V at t equals 2 seconds. Well, it's going to be Q over m times 30 times 2, which is 60, plus, I plug in 2 here, Q over m, 40 times 2 is 80. So we'll call this V initial and V final, and then the change in kinetic energy. And velocity squared is the dot product of the velocity vector with itself. Okay? And when you do this, you'll get the following. I'll let you do the algebra. Let's see. You get that expression. That's a M. That's a V naught. Okay? You all know how to take a dot product, right? This dot with itself is just going to be 3600. And then this is going to give you 6400 Q over M times plus V naught. Okay? Remember, a dot product gives you a scalar, not a vector. All right, problem number 4. We have a sphere. And it's at x equals 0. And the sphere is charged. And then we have a plane here at x equals 6r. 6 times the radius of the sphere. And the charge density for this sphere is A times r. First question, all it asks for, because people did all kind of calculations with this. What's the total charge on the sphere? It's a solid sphere. So Q is the integral of rho dV. Since the density only depends on r, then I'm just going to integrate over a bunch of spheres of thickness dr and surface area 4 pi r squared. My density, and then my surface area. And then when you integrate this, and that's all I wanted. This is a very conceptual question. Part B, what is this force on this sphere? Well, the total charge is that. We know that force equals Q times E. This has a negative surface charge density, so it means this is going to be attracted to this guy. We know the field due to a plane is sigma over 2 epsilon naught, and this field is going to be to the right. And so all I got to do is take this times this, and I'm done. That's all I wanted. Now, the last part says a positive point charge Q is placed at x equals 2r and released from rest. And we want to know, what is this change in kinetic energy when it goes from x equals 2r to x equals 4r. This might not be the scale, okay, but we use conservation of energy. Delta U plus delta K equals 0. Delta U equals minus delta K. Delta U is Q delta V. It starts from rest, so basically I'm just going to get Q delta V is minus 1/2 mv final squared. And really all I need to do now is find delta V. I need to find the delta V for this sphere and the delta V for this plane. So I'm going to do them separately and then combine them. Okay, delta V of the sphere, delta V is going to be delta V of the sphere plus delta V of the plane. Well, delta V of the sphere is going to be minus the integral of E dot ds. And I'll just I'll just call the charge on the sphere Q. I'll plug in the Q later. But the electric field due to the sphere, outside the sphere, is kq over r squared. And I'm going to integrate from 2r to 4r. Okay? And then delta V, this is the hard one, delta V for the plane. And for the plane, the field's defined relative to this point. So when you go from 2r to 4r, you're getting closer to it. You start at 4r and then you go to 2r. You see that? You start further away from it and then get closer. So you go from 4r to 2r. So for the plane, you're going to integrate sigma over 2 epsilon naught dx from 4r to 2r. There's a minus sign there. But here's the problem. We're going this way, our dx is getting smaller, so actually my dx is negative, so I actually have to put a minus sign there. You have to realize that if you're going in that direction, the potential has to decrease. So these two combined go in here. So let me erase this. So now let me put on in my expression for, in fact, let me move this to the other side of the equation. And so now I'm going to write my delta V's. Let's see, when I integrate this, I get a negative that comes out. So I'm just going to get kq over r. And then when I put the limits in, and then for the bottom one, when I do the bottom one, when I go from 4r to 2r, I'll get the following. Then you can substitute your q. And then you can have 1/2 mv final squared is equal to, actually, I'm sorry, I want the change in kinetic energy. So that's the change in kinetic energy anyway. Is going to be q times k pi a r cubed over 2 plus sigma over epsilon naught r. And I'm leaving the algebra for you. I'm going from here to here. Okay, so this is not a major step. I mean, once you have this, you're essentially done. Okay. Okay, I did the last two problems out of order because my printout is out of order. So really, I'm doing number 4. The last one I did was number 5. And this is just a straightforward calculating an electric field problem due to some charge distribution. You're given the charge distribution. You're given, and I apologize, I forgot to put in a lambda naught in there, but you're given lambda equals cosine of theta. So I guess we'll just proceed this way. I guess lambda naught's 1 in this problem. Okay. So I measure the angle with respect to the vertical in this case. A lot of people didn't pay attention to that. So if you draw the electric field vector due to a small dq here, this charge is positive. So the electric field's got to point this way. Now, on this end, this angle's negative, but the cosine of a negative number is a positive. That electric field component points that way. And what you see is that if I go to the same angle in the other direction, you can see that the x components will cancel and the total field points straight down. And so my r hat component, when I solve this problem, will be cosine of theta j hat. And I forgot the minus sign. Okay, minus cosine theta j hat. The other component of r hat, I'm not going to care about because I know when I integrate, I'm going to get 0. And so a lot of people miss that. So my job then is to find my expression for dE, which is k dq over r squared r hat. R squared, oops, is just the square of the radius of that portion of the ring. R dq is lambda dl, but this is an arc length. And lambda is just cosine of theta. So I'm pretty much ready to put this together because I know what r hat is. So E is going to be the integral. If this thing takes up 2/3, 2 pi over 3, then each half is pi over 3. So I'm going to integrate from minus pi over 3 to pi over 3 of k. dq is going to be lambda, which is going to be cosine of theta, r d theta over r squared times a negative cosine theta into j hat. So basically I'm going to integrate cosine squared. So let me pull some constants out. So all you got to do is integrate this. And so when you integrate this, you get the following. And I'll let you'll do the integral, just in the interest of time. Remember, I forgot to put in a lambda naught in this problem. That was my bad. So you didn't even have to evaluate lambda naught. Okay, so that's it. I know this first test is a hard one. The average wasn't very high, but it's kind of typical for this unit. Just hang in there, and the next exams I think you'll do better. So I hope this helps you. I didn't show all the steps to get to the final answer because I figured you're able to do the integral, and in some other cases I figured you were able to do the algebra. All right.